let's see. Let's see what we can do with this. So we played with this a little bit before, but geometrically, since that angle is 30 degrees and I have 10 feet down there, I could say the sine of, let's see, I guess it'd be tangent. I could say the tangent of 30 is the opposite length AC divided by the adjacent 10 feet. And if I punch that in, I get 5.774, which is also the same as 69.28 inches if I multiply 5.774 times 12. So notice that's a fixed distance. So no matter what happens with the weight, that distance right there is not changing. The 10 foot isn't changing, but AB is going to change. And again, I can figure out AB right now as well. I guess it'd be cosine. Cosine of 30 is adjacent, which is, maybe I'll just do this in inches. Adjacent, which is 120, 10 feet, 120 inches, divided by the hypotenuse, which is AB in this case. And so if I punch that in, I get 138.5641. So that's what's going on right now. Sitting there right now. But of course, if I actually add some W weight to it, that AB is going to stretch a little bit. And they told us something about how it would stretch. And so that's kind of the key that we're tackling right now. The fact that we understand what E is, and we can find stress and strain and all of that, we're actually now in a spot where we can literally look at a material, A36 steel, and kind of figure out exactly what's going to happen. Would probably be a better problem for us right now would be maybe the opposite of this, where in other words, you knew what W was. And we said, oh, it's got this much weight on it. And then we said, okay, based on the kind of the size of wire it is, how much is that going to stretch? That'd probably be a more natural question for us, just learning this. But keep in mind, the realistic side of this, as I said before, is kind of a weight limit thing. In other words, we want it to bend down for whatever reason, no more than 3/4 of an inch. And so then let's add a weight restriction to it. You know, what's this distributed load? What could it be? Okay, well, let's do this. Does the fact, and this, you got to read these carefully if you have a question like this, but it says it's 0.75 downward. In other words, B is going straight down, say to right there. And so in a sense, our 10-foot member is going to be down there. The question is, and again, I don't think this is obvious, but do you see that there's a right triangle in that? In other words, if I come over here and say, okay, cool, I've got this distance across the top. I've got this distance, it's just 0.75 inches. And I've got this distance right here, which hasn't changed. It's still 10 feet or 120 inches. And that does make a little right triangle right there. And so because I know two things about that right triangle, I can find everything I want to find. And I'll have to erase this just since it's going to make this drawing kind of a mess. But does it make sense if I took a line from here down to this location? Like that's the new location for AB because it's going to bend down there. Does that make sense? So there's more than one way I could do this. But since I've got this picture right here, and if I called this angle theta, then I could say, oh, that's opposite, and hypotenuse, that's sine. So I could say the sine of theta is 0.75 over 120. And if I do that, I get that that angle, if I need to know it for anything, is 0.3581. So it's not even half a degree. It didn't bend down very much. And you can probably appreciate from an engineering perspective, that's kind of what's going to happen a lot. Like it can't even see it. Like it bent a little bit, but you can't even really see that. It'd be hard to measure. So, okay, cool. So then, go ahead.
We subtract that from our 30 degrees, and that's our new.
Well, there's kind of more than one thing I could do. I'm gonna do this, like this is AB, which we said was or AC, which is 69.28 inches. That hasn't changed. And that distance is still 120 inches. And keep in mind, what I'm really after here is to try to figure out how long this cable is. I mean, we said 138.56 inches long, but we're going to put this weight on it and it's going to get longer, right? So I'm trying to draw a picture right now of where longer would be. So for instance, back here, and this is again kind of the language of this. If AB was 138.85, then this distance here we could call AB prime, which just means, hey, it's not the same anymore. L and L prime or something like that. So does it make sense? I don't know enough about that triangle. Like I need to know three things, and I don't like this triangle because it's not a right triangle. It's because like, excuse me, law of sines, law of cosines. I'm not as happy with this triangle as I was that red one a minute ago. But do I know one more thing?
Because of the other triangle, because of the red triangle.
Yeah, back up here, didn't I originally know that this was 90 and then it just grew by 0.35 degrees? So I actually do know this angle right here. It's 90.3581 degrees. I don't know if I need to be that accurate, but.
Wait, sorry, that I lost this triangle.
Yep. So this original triangle was a right triangle before we put weight on it. And then it bent down and got 0.3581 degrees bigger since this angle right here is theta. And so I do know two sides and one angle in this new non-right triangle. So you have an old note sheet on this, but now that I know 3 of the 6 parts of that triangle, I can solve for the last one. So I can actually know how much longer it got. Again, I'm not really sure exactly where I'm going with this. I just know I'm figuring out stuff that I can figure out. I think in the interest of time, I'm just gonna say here, law of cosines, not calculate it all, not write it all out. If you want to bug me about that after class or something, please do. But if you do that, you get 138.9375. What about that number is gratifying? I mean, we just did a bunch of calculations, right? Law of cosines is pretty big and ugly. Is that the kind of number you would have expected?
It only grew just a little bit from before. Yeah.
That's exactly right. It grew a hair longer. That kind of makes sense. So I'd expect it to be a little bit bigger. If it'd been something like 150, I would have thought, oh, that's kind of weird. That's pretty huge. It's hard to believe. It didn't get that much longer. So definitely longer, not that much longer. It kind of feels like, oh, okay, probably didn't screw that up. That's kind of cool.
So the Pythagorean theorem is only for right.
Correct. Yeah, and interestingly, law of cosines is the Pythagorean theorem. In other words, the hypotenuse squared equals the other two squared and added together. Uh-huh. Yep.
What do you care? Your program's just gonna forget after
Yeah,
like 2 months.
But it goes on to say, because this isn't a right triangle, minus 2 times one of those numbers times the other number times the cosine of the angle across from the one you chose to put alone. The one you chose to put alone is across from the one angle that you know. So yeah, it's a Pythagorean theorem with a little bit extra to it. Interestingly, this works on right triangles too, but cosine of 90 is actually 0. So it makes that whole last term go away. When it's 90, it just doesn't go away. So again, mathematicians love this kind of stuff because this is like the formula that works for all triangles, and the right triangles just get thrown in there, but it's kind of like, this is better than the Pythagorean theorem. I don't know if you've ever thought about it that way before. Works for all triangles. Okay, cool. Now, notice I now know how much this thing grew. Again, I don't know if I necessarily need this, but remember, again, I apologize for those of you that just came out of the last class, but strain. This is killing me too, if it's any consolation. Strain is the percent something grew, right? Again, that's a little tricky. It's how much it grew from what it used to be. So in order to get how much it grew, don't I have to take what it became? 138.9375. That's how long it is now, and it was 138.5641. So notice the difference of those is really tiny, like 0.4. It only grew like 0.4 inches, divided by which one of those two numbers? The original. So if I don't chunk that, I get epsilon is 0.0027. That is not a percent right now. If it was, you'd move it 2 decimal places to the right, it'd be 0.27%. It's like 1/4%. So again, this did not get longer in any way that you're going to see. And that's should be the case in engineering for the most part. You should not see it get longer. It shouldn't. Kind of makes sense. Now, what we learned recently that's so cool is there's a relationship between shear strain and normal, right? This relationship we learned, and there's more than one way to write this down, but we learned that there's more than one way to write this, but I'm going to write it this way. We learned that strain, I'm saying this just because like you, like me, you're probably still kind of trying to get all of this down, like there's the letters and the concepts and all that. It's like, God, it's so hard to keep straight. So the main concept last time was that if you stress something like we're doing here, we're putting all this weight on it, it's going and get longer. We put stress on it. As a result, it strains and gets 1% longer than it used to be. And we learned last time that relationship is linear as long as you stay in that proportional area of the graph. And what makes them equal is this E, this modulus of elasticity. And so anytime I know the strain, like we just found out, I could always convert that over to the stress if I happen to want to know that. Now, why do I generally want to know that? Because those are the kinds of things I can look up in tables and so forth. So the relationship between stress and strain is powerful. Strain is like, uh-oh, it got too big and now it broke. I don't want too much strain. And then, well, if that's the case, then how much stress is going to cause that much strain? And so these are intimately related concepts. So cool. So I know that number. Do I know E? Do I know the modulus? Well, I can look it up. They didn't tell me here, but they told me this is A36 steel. So I can look that up in the back. This is in the back of your book. I made a page for this. I can't remember if I posted this. If you happen to just want a physical copy of this, all I did is snap pictures, so to speak, out of the back of your book. I couldn't find this online, so I literally did it with my phone and just PDF'd it. Let's see, we were working in, remember there was US customary, and then there was sort of the SI metric. So because we had feet and inches and that stuff, we're up here. So we said, and I have it highlighted still from last time, modulus of elasticity is up there, and I need A36 steel. And so we said, oh, look at that. I mean, that was one of the ones we looked at last time, just coincidentally. And remember, that's 29, it says up there, times 10 to the third KSI. So it's actually 29 million PSI, huge number. And that's part of what this experiment's going to be here in a minute. We're going to calculate E for one of these pieces of wood, like actually figure it out. Instead of just looking it up in a table. Oh, cool. So I know E, 29 million. Awesome. Looked it up. So now I can go back to my problem and insert that. Again, I haven't even read the question. I don't really know what I'm even calculating. I'm just figuring stuff out because I can, because it's fun. So I have 29. I'm going to write 10 to the 6th PSI there because I want inches and pounds. I get all confused when it's kilos and kips and all that stuff. So that's just personal bent. And then what's the unit for epsilon? Yeah, it's either nothing or millimeters over millimeters, or maybe in this case, inches over inches. And so it ends up unitless. But what it means is every inch, what it's telling us is every inch of that original piece is going to grow by 0.0227 inches. It's that many inches per inch. So if I took that times its original length, then I would know actually how much it's going to grow completely. So inches per inch makes a total ton of sense. So it is no unit at all. Notice if it's no unit at all, it means sigma over there is pounds per square inch too. And that's what we were kind of looking at. So, oh, okay, I'm just taking 29 million PSI and I'm going to get sigma in PSI. So 29, 1, 2, 3, 4, 5, 6 zeros. Try to do this somewhere. Times 0.0027. I got sigma is 78,300, and this isn't a rounding kind of an issue, but 78,300 PSI. That's what sigma is. Now stop and think about that a minute. It's basically saying that's how much, not force, but force per area. That's how much force per area that cable can handle. That's how much force is, well, must have been on it. That's how much force per square inch must have been on it to get longer like it did. Does that make sense? We were just told it got longer. We don't know how. It just got longer. Go ahead, Connor.
So this is calculating up until, I don't have my chart, I left my notes at home, but this is calculating up until the linear, the point where it's like, what am I trying to think of? The
Yeah,
probability limit? Yeah.
The
limit, right?
proportional.
The proportional, thank you.
Yeah.
So is this telling us, because I'm looking at this whole equation, that it will grow 0.0027 inches until it hits the proportional limit? Oh, from the chart.
No, because we don't have the chart in front of us, we don't know what its yield, what its sigma PL was. Because if we stressed it too much, then it goes bow, and then it never goes back again. So this is assuming we've kept it inside where it belongs. That's exactly right. So in other words, if you take the weight off, it goes right back to what it used to be. No, nothing got hurt.
Right.
So we're in there somewhere, but we have no idea where that is.
We're still in the last.
Yes, we're in the elastic region. It's very complicated. So of course that could be called, uh-oh, something's wrong here. I have too many zeros in that. Actually went in yesterday and took a flight physical, and because you can't fly unless you have to have a physical every so often to make sure you don't crash and kill everybody, I guess. I need new glasses is what I learned. I barely passed it vision wise. I'm looking at this
They're
right
like,
now.
all right, Doug, cough. You're like, why do I have to do this for a flight?
I'm just, that's the whole scenario stuff in my head.
Me and my buddy, because we had to do physicals for basketball and stuff. My dog always like stuck a finger like in my ball sack, told me to cough. And my buddy was like, "Oh, don't you hate like physicals?" And he like held his hand like a cup like that. I was like, "What are you doing?" He's like, "That's how the doctor." And I'm like, "Bro, your doctor's fondling you." Like, that is weird. That doesn't happen to me. He's like, "What did your doctor do?" I'm like, "Finger." And he's just like,
That's totally funny. You got to be careful what you do in secret. You know?
yeah, that's what I do. Doctors
It's
not doing
gonna
it.
get heard.
I'm gonna report this, sir.
So the question is, do you understand what that sigma is? And again, I feel like this is hard. Like we've learned a lot of things. This is not just going to come to you immediately. Does it make sense that that PSI number, by its very definition, pounds per square inch, you know, that's literally a fractional number. Well, that's what sigma is. It's how many pounds do you have of normal force divided by the area. That was one of our formulas for that. That makes sense why it would be the case. And so the question is, well, how many pounds do I have and how many square inches do I have? Well, I just figured out I have 78,300 pounds. I don't know what normal force that is, but I do know the size of my cable. See, that's what's so important here. Because just saying, oh, I chose this good material. Well, if it's too small, it doesn't mean it's not going to break. So we were told earlier that that had a diameter of 0.2 inches. So, and they said diameter, therefore it's circular, and then that's tricky in some of the problems. What shape is it? It's circular, so we said if you take pi divided by 4 times the diameter squared, that'll give you the area. And so notice this is actually going to turn, it's going to turn that PSI number into an actual force, how much force is on the cable itself. Now, in the end, there's part of me that doesn't care, because if I could look that up in a table and I was told, yeah, that can handle 100,000 PSI, then I would go, oh, look, 78 less, I'm good. But in our case, we have to turn this into pounds, not pounds per square inch, because we're trying to work our way back to how many pounds were on the beam down there that was causing all these problems, right? So if I take that 78,300 and multiply it by pi, and then divide by 4, and then multiply it by 0.2 squared, I get that the normal force on that cable is 2459.9. I'll just call it 2460. So in other words, we just figured out exactly how much, pull there was on that cable that caused all this to happen. We were told how much it went down experimentally, which is about what we're about to do here. And then we worked backwards to figure out how much force was on that cable itself. Okay, cool. Well, now let's consider this, like what's going on here. So that means here's our bar, our cable was in here at 30 degrees, and we just figured out that that was being pulled on this hard, right? What do we do?
You have to find the X portion of that. And then you can find the horizontal force of the bar, find the overall W.
Yeah, so because this whole thing is static from last term and it actually isn't rotating, I can get out of this mess by, or actually convert to that W. And again, I'm going to rewrite it here, that measurement, because of the way it's written is not pounds, but pounds per foot, or pounds per, I guess I got to think about this. It could be pounds per inch. Let's see, is it just automatically pounds per foot, or can I just say pounds per inch? I guess I could probably do whatever I want.
As long as the CB is used in inch, pound per inch, vice versa, please.
So I'm going to make the sum of the moments around C be equal to 0, because that's what's going to happen if it doesn't break, and that's going to allow me to figure out what that is now that I know that force. Notice though, the cable distance, I mean, if I am working this in feet, this is 10 feet. It's not 2446, right? Because it's not perpendicular. Remember, the force, it's got to be perpendicular to the distance. So I can say 2446, and that's in the positive direction, but that's going to be modified, since this is a 30-degree angle, by the sine, right? Let's see, by the sine of 30. Do you agree with that? So effectively, that's this right here. Yeah, it's the y portion of that. And then that's a distance of 10 feet away. So notice that's foot pounds. And then, so that wants it to go counterclockwise, positive. But then we have this blue force, W.
Which is down.
But remember, we've got to replace this. We can't have all those forces. There's millions of them. So we get to replace this with just one. What do we do to replace that with just one force?
W times its length divided by 2. No. W times its length, and then the distance is divided by 2.
Yeah, notice the units there. If you take That's why W is pounds per foot. If you have basically, say W is 50, if you have 50 pounds every foot has got 50 pounds on it. Then if I take pounds per foot times 10 feet, then those cancel and you just get pounds. So do you see why that unit has to be pounds per foot, not just pounds? Because if it was just pounds, it'd be pounds times 10 feet, and it'd be foot pounds, it'd be torque already. So W times 10 is actually giving me how much does all that weigh combined. Now I have that weight, 10W. How far away is that?
Halfway through, since it's rectangular.
Yeah. So it's right in the middle, since those are evenly distributed. It's right in the center of that. And so all of that would have to be 0. And so that's going to allow me to find W. That's the only thing I don't know. So let's see, 2446 times the sine of 30 times 10. Add that W10 5 to the other side. That'd be W times 50. If I divide by 50, I get like 245.
For some reason, I want to assume there's a force applying a B line.
Where?
I don't know, for some reason I'm looking at it and I want to put an arrow underneath B and symbolize it as B line.
Yep, why not?
But that wouldn't make sense, would it?
Not in this case because it's not sitting on anything. Does that make sense? Usually we had it sitting over here, sitting on something, and so that was helping. But here there's nothing. It's just cantilevered out. There's nothing over there.
And
So the only thing holding that up is that BA force. So again, this to me is a problem you need to go back and kind of stare at, because I ended up making a lot of calculations for this. And in a sense, I got lucky in the sense that it kind of flowed and everything I needed. But notice we just created a, if you will, a weight limit for this. If this was some product inside somebody's shop, we could say that's your max. And notice that's a distributed load. We could say times 10 and say it's 2,450 pounds as a point load, but does it make sense it would matter where it was? So this is limited to a distributed load. And again, that's kind of the way houses typically are, because it's live. In other words, you're going to move it all over and it's going to be everywhere.
I'm just trying to wrap my brain around kind of what we're finding. So when you have that 78,300 PSI, that's just, we're going to say that's the max weight that cable can hold.
That is, yeah, it's the max stress, and it's weight and in consideration of area, weight and area combined, pounds per square inch. It's like a 2-unit PSI is kind of a 2-unit answer. And again, I find that confusing. It's not the weight. Actually, the weight turned out to be 2446.
Right.
The actual weight on the cable was that. But then if you took that and divided by its area, then you'd get 78,300 PSI. And it's that you usually look up in tables. It's the PSI strength of a particular material. Because you can imagine if you went to a shop and said, hey, can you make me, some weird shaped item? If you know the PSI, then you can find the area of that weird shape that they made and still use it.
Right.
Because they can't have a chart that has every single shape that anybody ever made. Does that make sense? But if you have a PSI number, then you can convert it.
So basically what we did was we said, we have a cable with the length specified, that's the PSI. And then based on that, this is the weight you can have on that beam.
That's right.
Okay.
Yeah. And again, it's kind of a weird problem because they just told us it went down 0.75. Well, stuff doesn't go down 0.75 unless there's weight on it. So this is a bit backwards in a sense. But one of the main things to take away from this is this right here. Just the fact that if you have stress, you have strain. You got one, you got the other one automatically. As long as you know what material it is and can look up that E value someplace in a chart. Does that make sense? So study this example with respect to what is this, chapter 3 questions. This is that's kind of the end of what you need to know for chapter 3. And as far as your assignment's concerned, that's really only 3.4. Like you should be able to do the 3.4 questions now.
questions do we
There's 8 in 3.4. And so 3.7, we're going to end up talking about that Tuesday. So really what you need to, if you want to be caught up, you do 3.4.
So it's basically a chapter 2, but with specific materials.
Yeah, that's exactly right. So basically in the first chapter, we figured out how stress worked. And then in chapter 2, we figured out how strain worked. In chapter 3, we figured out they don't have to be related to each other. And now we're getting serious in the sense that we can now literally choose materials, make calculations, and predict how much longer they're going to get before we even build things, which is amazing. It's so freaking awesome. So what you want to be done with 3.4 when you come back. What I mean by that is at the end of your limit. There'll be tricky problems, there'll be things that don't make sense. Again, run me down, send me a text anytime between now and the next class. Ask me for a hint, come into class or come to school. Like this class, for instance, I'm sitting in here half an hour before class most of the time, for your sake. The rest of you guys are coming in, but I'm in my office all morning, like from 8 o'clock until 11 when I come in here. So I'd love to spend some one-on-one time and kind of help you think these things through. Because again, I've told you this, one of the reasons I admitted to you guys, I'm a chapter or two ahead of you guys, because it's like, this is hard for me to get my mind around too. And I've been thinking about this a lot. And there's so many formulas, but it does reduce to, I try to make my note sheets really compact. Everything you need is right there. And if you just use the formulas that are in front of you and figure out everything you can figure out, you'll get the answer in the end. But the part I think I can help with is just the conceptual understanding of what these two things do. And what I've highlighted there in that classic E epsilon sigma equation is the whole business of engineering, and at least specific to what materials do I pick and how do they behave. Okay. So, and all I really want to do with this project is